Hello everyone. So today we are going to discuss about the next part of the isolated footing design. So far what we have discussed, we have calculated out the depth of the footing, which is calculated using the concepts of one-way shear and two-way shear or punching shear, right? So one-way shear, the critical phase was at a distance d. D is the effective depth of the footing, and the punching shear is the critical faces at a distance d by 2 from the face of the column all around the column, right? So this distance is d by 2, where d is the effective depth of the footing. Okay, so far we have found out that for our footing the d overall depth of 500 is sufficient. So now we will go for finding out the effective depth of the long span as well as in a short span. Why we have calculated two different types of effective depth? Because as already I have mentioned probably in slab design, that one layer of steel will be in this direction, right? So this will take care of the moment, suppose in this direction, suppose this is the x and y is in the other direction. So and then the other reinforcement will be placed just over the previous layer of reinforcement, right? So in that case, for the first layer of reinforcement, the d, this is suppose dy, which will be the distance up to the center of the reinforcement of the bottom layer, and suppose dx, which will be taking care of the moment about the x direction, that will be taken care of by the dx, the effective direction in the x direction, which will be the distance of the center of the reinforcement, which is at the top layer, right? Which is above the bottom layer. So obviously you can see here dy and dx are not same. Over here dx is less than dy. So that is why basically we have calculated two different types of effective depth considering the long span as well as the short span. So here dy, initially if I consider the long span, because for the long span the reinforcement will be provided at the bottom, or the first layer will be for the long span. So the effective depth found out to be d minus 75 which is the clear cover, minus the diameter, half the diameter of the bar, and it comes out to be 417 Okay, then effective depth for the shorter span, that means this layer of reinforcement will just come above to the reinforcement which is already being provided for the long span. So short span reinforcement will be, so the whatever already you have dy, that will be subtracted. um, that means the half of the reinforcement dia, and again half of the top reinforcement dia, then you will get the dx. So I think you can visualize it. Suppose this is our footing, this is the first layer, okay, of the reinforcement. So if this is the suppose center of this footing, so this is nothing but dy. Okay, dy is what? Dy is equal to the effective depth minus the clear cover minus the half the diameter of the bar, right? 5 by 2. So it comes out to be up to here. Then the next layer of the bar, which will be the top for the shorter direction, it will be here, right? So if you want to find out up to the center of this bar, so this is dx. So dx will be how much? Dy minus, so minus the half of the bar that is remaining at the top, so the 5 by 2, 5 is the diameter of the bar, then again minus 5 by 2 you have to do, then you will get the dx, right? So dx is equal to dy minus 5 by 2, then it will come to this top layer of top edge of the top of the bottom reinforcement, and to the center of the top reinforcement you will again have to subtract 5 by 2. So this is the diameter of the top reinforcement, and this is the diameter of the bar of the bottom reinforcement. Okay, so like that we can find out the depth of the reinforcement to the means to the top reinforcement, right? So dx and dy, that is why we calculated two different effective depths, which is, this is dy is for long span and dx is for short span. Okay, so now let us find out what is the maximum soil pressure because of the loading as well as the dimension that we have taken. So for our case, the dimension B and L we have already considered, right? So and the D also we know now. so we can find out the what is the max shear stress or the maximum pressure that is acting on the soil. And if suppose we consider that the unit weight of concrete is 25 kilonewton per meter cube, and for soil it is 18 kilonewton per meter cube. So now if you find out the total load, that is PUC, which is a basically we can say this is the design load, right? This is the design load. And you already know, to find out the pressure in the soil we do not need the design load, we only need the working load. So that PU will be divided by 1.5, so that it becomes trans to working load, then divided by L by B, L into B. So this will give you the pressure because of the point load. Okay. Then we have the concrete, that is self weight of the footing. So gamma concrete into D. This will give you the self weight. Okay. Then we have the self weight of the soil which is above the footing, because suppose you have excavated certain portion of the land, then you have constructed the footing over here, then you will pour sand over the footing, right? So this sand or the soil will have certain weight. So what the weight of the soil will be gamma soil into df minus d. So this will give you the weight of the soil, because the pressure because of the soil. Then mux, this is the moment that is acting on the footing, divided by the 1.5, because to convert it to working load, and as well as this is the section modulus BL square by 6, right? So from this you can find out that the soil or the soil pressure is 202.038. And if you remember, the SBC was for our case was 200 kilonewton per meter square. So you can see it is slightly more than what we have the safe bearing capacity, but already you know that the safe bearing capacity is being considered with a factor of safety of 2.5. So as it is slightly more than that, we can accept it for our design. Okay, so we can say that though it's only 2 kilonewton per meter square of load that is exceeding, and already we have factor of safety of 2.5, so most probably it will be safe, so we can accept this particular value or particular dimension of the footing. Okay. So but it is always advisable to have the stress, this particular stress value, always less than the safe bearing capacity that is already provided to you. Okay. So but if even if it is slightly increasing, suppose 1 or 2 2 kilonewton per meter square, it can be it is acceptable. Okay. So now we will go for design of the flexural reinforcement. So we know that for we have the footing, or if you see the top view of the footing, we have two spans, right? One is long span over here and one is short span. So we have to design the reinforcement for both long span as well as the short span. We know that the reinforcement for the long span will be in this direction at the first layer of the reinforcement, and for the short span, whatever moment come, whatever reinforcement you will be providing in this shorter direction, right? And this will be at the top layer. Okay. So first let us design for the longer span. So for the longer span, as you can see here in the figure, the cantilever portion is 975 right? So this much is the cantilever projection for this particular footing in the longer side. And the B, that is the width of this footing, is that we have assumed is 2000 right? And dy, that is the depth of the footing in the longer direction, we have already calculated out as we 417 and maximum stress, that is also we have found out, that is to 0.264 newton per square. You can also see in the figure also, I think this has already been calculated out. Then we can the thing is that you first need to know where actually the moment you will be calculating, because as you can see over here, this is the footing diagram. And you already know that for one way shear it is at the distance d, for punching shear it is at the distance d by 2, and for moment calculation, the critical phase will be at the face of the column. Okay, it will be at the face of column. So this is the face of the column. That is why we needed the cantilever projection, because here you have to find out what is the stress. This stress portion you need to know. Then this is a trapezoidal distribution of forces, and you have to find out the load, or this, because of this particular stress or the force, upward force, how much moment is acting over this cantilever portion, that you need to calculate out. And to take care of this particular moment, you have to provide reinforcement. Okay, so that is what we are going to do now. We just not need to find out what is the, at this critical phase, because of the moment, what is the stress value we need to find out. So you know that the minimum stress is 144 and maximum stress is 264 kilonewton per meter square, right? So you need to just do the interpolation and find out the what is the stress over at the face of the column. So that is what he has done here. So the QU column is nothing but the stress at at the face of the column. So you can just do the interpolation. You just I have just used the equations. It is nothing but the interpolation. So Q minimum, this is 0.4011, that is 144 kilonewton per meter square, plus whatever variations that you have for this particular portion. I think no need to explain this interpolation. You can do it by yourself, and after doing interpolation, you can find out that the stress at the face of the column is find out to be 0.216 Newton per mm square. Okay, so this is the value of the stress which is acting at the face of the column. So we know this, the trapezoid, we know the distance of the trapezoid and the two distances of these two particular sides. One side is having a dimension of 0.216 and other side is having 0.264 kilonewton per, sorry, Newton per mm square. So you can find out the total reaction force F for this particular trapezoid, right? So that can be done by what you can do. So this trapezoid, you can divide it as a triangle, as an one and the other one as a rectangle. So for this rectangular portion, you can directly see that this dimension is 0.216, that is QU column. So 0.216 into what you can do here, if I want to find out the moment over here at this particular phase. Okay, I think I should mention it again. Suppose I just particular portion of the trapezoid or the force or the shear distribution or the force distribution, I just draw it here. Okay, so this value is 0.216 and this value is 0.264. Okay, so now this particular trapezoid can be divided into a rectangular part as well as a triangular part. So first let us consider this particular rectangular part. So this rectangular part, I want to find out a moment about this side, right? And this is nothing but small c, which is around 975 mm. Okay, so let us first consider the rectangular part. So you can see that it is 216.216 Newton per mm square into the distance, which is 975, right? So it will be give you the area of this particular rectangle, and you know that the force for the rectangle will act at the center of this distance, that is c by 2, at the distance of c by 2, that is 975 by 2. So this will give you the moment and in Newton mm, right? So this will be the moment for this rectangular portion. Then if you want to find out the, for the triangular portion, so the area of the triangle is half into the length into the height. The height is basically here, this portion is the height here, so it will be the difference of 0.264 minus 0.216, right? So this will give you the total area of this triangle, and where this force or the resultant of a triangle walks, so it will work at the distance of two third from the apex, right? So two-third of the apex or the total length or the height of the triangle is 975. So this will give you the moment from the triangular part. Okay, this is what exactly done in this particular equations. So as you know that I am using this MATCAD software, so I have already defined what is C. C is the cantilever projection, B is the width and all. So so that is why I have just written the equation. So you can also directly write the numerical values. So that is what I have done over here. The only thing is that B is being multiplied, so that because you can see here this load or the stress is in Newton per meter square, sorry, mm square, and this will give you only in a unit width, right? And we have a B, so width is B over here. So if I want to find out the total force all along the B, I have to multiply the B on both the components of the rectangular as well as the triangular moments. Okay, so this is the actual moment that comes out to be 235.893 kilonewton meter. Okay, so this is the moment that will be acting for this whole cantilever projection part, okay, at the face of the column. So we have to take care of this particular moment. And also someone you or some of you might ask, why to not take this portion of the stress distribution. But here you can see that the stress distribution on this side is smaller and stress distribution on the other side is larger, right? So obviously the moment will be more compared to the moment calculated on the other side. So that is why always take the larger portion, or where the moment will be more, consider that portion, okay. So and also I would suggest that always visualize the stress distribution, as well as always try to visualize the stress distribution, and then try to find out the forces, because then it will be very easier for you. Then we have the moment with us, then we can just find out the area of the steel, the same equation, same old equation. FCK here already we have considered for footing, so FCKF into B into dy. So I think you already know this. So we found out the area of the steel required for this particular moment is around 1633.262 mm square, okay. And let's now find out what is the minimum requirement of the steel. So minimum requirement is 0.12% of steel. It is the same as say suppose the flat slab, it is same as flat slab, right? It is, if it is mild steel, it is 0.15%, and if it's a HYSD bar, it is 0.12%. So that is what you have to do. Minimum steel is coming out to be 1000 mm square, and we require is 1600. So obviously the requirement will be more. And also, as you remember that while calculating the shear strength, right? Shear strength, tau c values, we have assumed that if you see the previous videos also, you will see that we have assumed that the percentage of steel as 0.25%, okay. So let's, as already we have assumed, and assuming this 0.25%, we have calculated the shear strength, so that we have to provide this one. Otherwise our whatever assumptions we have made and calculated the depth of the footing, that will be wrong, right? So 0.25% is minimum you have to provide, as because that much you have assumed, and for assuming that, we have found out a tau c, and from the tau c, that is the shear strength of the concrete, we have calculated the depth of the footing, right? So you cannot place reinforcement which is less than 0.5%. So let's say for 0.5%, how much of steel will be required. So it is coming out to be 2085 mm square. Obviously this is more than what is required, so we are going to provide this much of, that is 0.25% of steel. So considering phi as 16 mm diameter of the bar, so how many numbers of bars will be required for this whole distance? Because we have calculated, it is the whole moment we have calculated is not for per unit meter. We already multiplied b with the while calculating the moment, so it will be all along the, all for the whole footing, right? So the for the whole footing, the reinforcement is coming out to be 10.37. So that much means in fraction you cannot provide, so let us provide 11 numbers of bars along the longer side of the footing. Okay, so let's see what is the spacing is sufficient or not. So if you find out the spacing, the clear spacing is coming out to be 167 per 4 mm, so it is okay. So it is not, means not more than 300 mm and all, so it is okay. So now means you can write provide 11 numbers of 16 mm bar along the longer side, okay. So I think this is very clear for you, this is not that tough. And yeah, then the next thing is that as we are now only calculating the reinforcement for the longer side, always remember that in case of beam also we have discussed that while you are providing the reinforcement at the beam column joint, you have to provide some development length, right? So here also if you'll see that because of the upward reaction of the soil, the whole footing might deflect something like this, right? The footing might get deflected something like this. With this, what will happen, that whatever reinforcement you have, that will be under tension, right? So in that case, what might happen if the strain or yeah, the strain variation of the concrete as well as the steel, if it's not same, what might happen, that is there will be relative displacement or a relative, yeah, or dislocation of the concrete from the from the of the steel from the concrete, right? In that case, what will happen, that steel will no longer be an integral part of the concrete, and all the assumptions that we are making, that will be of no use. So that is why we need to find out the development length, whether whatever reinforcement we have provided, it is sufficient or not to take care of, or so that the steel remain as an integral part of the concrete, or it doesn't come out because of this particular moment when it's going to act on the footing. Okay, so that is why you need to find out the development length. So let's see. So for FCKF, that is the footing grade is 20 M20, and tau BD value we will find out as 0.12, that you can find out from clause number 26.2.1.1. And as we are using HY as the bar, this tau BD will be increased, can be increased by 60%. So from that we can find out the development length, and development length equations already we have calculated, so I'm not going to explain all this. So LD comes out to be around 752 mm, and you can see that the tau C, sorry, the cantilever projection is around 975 mm, right? The available length, the cantilever projection is 975, and the requirement is development length requirement is 750. So obviously we have more space available compared to what is required, so that means our development length criteria will be satisfied. Okay, so LD is less than the available length, so it will be okay. So like that, you have to check for the reinforcement in the shorter direction also. The same process in the shorter span. Now you need to find out what is the cantilever projection in the shorter span. You just look at the plan, just draw the plan and find out what is the shorter span, because you know that this is 2000 mm, right? The column is I think 300 mm, so you can find out what is this projection, this cantilever projection. So for this, now just try to visualize the stress distribution you have. So you know that the moment is acting in this direction, right? So let me draw it clearly, sorry. Yeah, the moment is acting like this, so obviously the stress distribution will be something like this, and it will be varying all along the width, that is all along the 2 meter of this particular footing. Okay, so now as we are now calculating for this particular shorter span, the now you have to calculate the moment, right? So for this moment you can see that the stress distribution for this edge, this one, or all the this portion, or for a whole portion, will be just like this one, right? Like this one particular trapezoid. Okay, so this whole portion, the trapezoidal distribution you will see. So it is not similar to what we have in the longer side, because in the longer side we have a distribution something like this portion of reinforced distribution was acting in the longer side, but now in the shorter side you will be having the whole of the triangular whole of the distribution is going to act. So that is why what we are going to do, we are going to find out the average stress. Okay, the average stress you can just find out by taking the maximum plus the minimum divided by 2, and then the average, actually we have already calculated the average, which is coming out to be 0.204 Newton per mm square. Okay, over here I think at the center, at this portion, this will be 0.204 Newton per mm square. Then we can use this one, and we can find out average stress. So the stress at the face of the column, so at this location, what will be the stress? This will be Q max plus Q average by 2, which is 0.234 Newton per mm square. Yeah, so now you can see that the stresses that we have over here, this is the average stress we have. Now we are going to consider slightly more than that. Okay, so as you know that the stress distribution is something like this kind of stress distribution all along, right? So all along, suppose this is the drawing we had. So all along, all these lines you can see, this is the top view. So if I means if you see the isometric view of this line, so this will look like this. Okay, so all along this whole length we have this distribution. So we though we have the average of 0.204 Newton per m square, so let us take a slightly more greater value and take the max average of what is the average of this drawing, that is Q average is 0.204, which is over here, right? And maximum is 0.264, right? So let's take the average of these two and that will be taken as to calculation of the moment. So this is the average that comes out to be 0.234. And if I calculate the moment in a sorted direction, so that will be this particular load into the area will be nothing but this is the C short. Okay, this is a C short. So this is the width into the length is L. So C short into the length will be the area into this force, that will be total force, into the lever arm will be C short by 2. Okay, so this moment is around 207 kilonewton meter. Now if you find out the area of the steel, which is over here, you can see requirement is around 1477 and minimum steel is 1470. And yeah, so I think this should be dy. Okay, this should be dx. Okay, so now you can find out the numbers of bars, which is around 13 numbers of bars. We can provide 14 bars. Okay, so here we have not, you will see that we have not looked for that is 0.25%, because you know that all this mm, one way share and all, we have considered the 0.25%, because in the one side if it is 0.25%, obviously on the other side also it will be, means only one side, and tension still is considered. So in one side we have considered, so on the other side we no need to consider this one. Okay, so if suppose the moment is on the both the side direction mx and my, in that direction, in that case probably you need to consider this particular 0.25% also. Okay, so as in our question only in the one direction we have the moment, so in the other direction we do not have, so no need to consider this 0.25%. So whatever is there, we provide check for the minimum one and provide appropriate numbers of reinforcement. Okay, so these 14 numbers of bars will be all along the whole length of the footing. So let us provide 14 numbers of 12 bars, and also let's check for the development length, which is similar to what we have done, and it is found to be satisfactory. And after all that, you can finally draw the detailed drawing of this footing. So we have, this is the longest cross section basically. So we have these are the bars. You can see the bottom bars are for the longer side, and the top bars are for this particular top bars. These bars are in the from for the shorter direction. Okay, and the xty you can see over here. So we have, for the longer side we have here 11 numbers of 16 bar, and for the shorter side we have 14 numbers of 12 bars. And this is how basically the final reinforcement will be provided. The column reinforcement will be extended, and this is basically considering the bearing, and this also, this length should be equal to the development length. Okay, this length should be equal to development length. So this is how basically the footing design is done, and I hope you have understood. Please go through the problems that are available in Pill and Menon, as well as the other books that you preferred. Whatever book you see for structural the analysis, or sorry, the RCC design, so you will find the footing design in all kind of books. So please go through, and if you want, you can see the videos for NPTEL and also. And if you have any doubt, please let me know. Okay, thank you.